Hello, thanks for coming. I'm going to start this talk by just getting you to think a little bit about the objects you use in everyday life. Next. Next. Okay, so this is an example of the objects that Gemma, who is a cook, uses every day. So you can see there all of the different cooking utensils. She's also a mother, and so you can see that there's a scooter and children's clothes. Next. And then here's an example of the objects that David, a third-generation cowboy working at the ranch in Tucson, Arizona, uses every day. I bet now you're probably sitting in front of a computer, and you might have used a mouse to click the link to this talk, and you might have typed already in the chat using a keyboard. And you might have a mug of tea or coffee or squash next to you, which you're going to reach and grasp. And also, you probably went into a room using a door handle. And the point is that we use thousands of objects every day without really thinking about it. And we take it for granted, right? Probably until something goes wrong. So our research is looking at how our brain controls our hand actions to interact with these objects. Okay, so just start with a short task. So hopefully you can do this at home. And I'd like you to just lay both of your hands in front of you. And I'm going to present some objects that are either kitchen items or tools. So there'll be objects that you can't find in the kitchen. And what I'd like you to do, as fast as you can, is pantomime how you'd grasp each object. So if it's a kitchen item, you could use your left hand. And if it's a tool, use your right hand. So when you're ready, 3, 2, 1, go. Stop. So how did that feel? There might have been some that were maybe a bit more difficult than others. So the tool. So I asked you to grasp the tool with your right hand. And here, this is an example of one that might have been a bit more tricky, right? So the handle of the object is facing the other way. Whereas if it was that way, it might have felt a bit more natural. And basically, whenever we look at objects, we not only process the shape, size, colour of them, but we also automatically perceive how we can interact with the object. So how does the brain see? So basically, when we see an object, the information travels through to our eyes and then all the way to the back of our brain to an area called the early visual cortex or primary visual cortex. And at this point, it's only very basic information about the scene in front of us. And the information from the early visual cortex travels down 2 streams. So one of them is the ventral perception stream, and that's involved in how we recognize objects. And the other stream goes up over the top, and that's called the dorsal action stream, and that is involved in how we control how we grasp the object. So how do we know about this? So we find out a lot of information about how the brain works by finding out what people who've experienced brain injury and the difficulties that they experience. So we know that people who've experienced damage in the ventral perception stream find that they can see and draw the objects, but they don't recognize what they are. It's a thing called visual formagnosia. And then when there's damage to the dorsal action stream, it affects our hand actions and our visually guided motor control. And one example is that people might know what a tool is, but not be able to use it correctly. So you can see there that the person with the comb is using it the wrong way around. So also we can find out how the brain works by using an MRI scanner. So here's our one at the UEA, and the MRI scanner is basically a big magnet, and it's really strong. It's 60,000 times stronger than the magnetic field of the Earth, and it uses magnets and radio waves and computers to take pictures of the brain. but also we can see which areas light up in the brain as well. So that's the areas that become more active. So basically, we can like put participants in a scanner, and they can lie there and watch objects come up on the screen like on a little TV that's projected through a mirror, and we take the activation level in each brain area. So what do we look at? We specifically look at tools, and tools are quite special because they're linked to like specific predictable action routines. So imagine a hammer. You're not going to use a hammer to stir a cup of tea or cut an object. You're just going to hammer. And then a saw, you're not going to use that for hammering, but it's a specific action routine where you're just going forward and backwards. And it's also something that is quite unique to humans. We are like the only species to constantly engage in like complex tool use. So when you wake up in the morning, you brush your teeth. We use a toothbrush to brush your teeth. You'll use a hairbrush to brush your hair, and then you'll eat your cereal with a spoon. And we're constantly using these tools every day. And they also involve both our ventral perception stream and our dorsal action stream. So we conducted a study recently in an MRI scanner, and participants were lying in there with the objects presented on the TV. So we presented them with either tools that you would rotate, so a key, but also things like a corkscrew that you're going to rotate, and also objects that they could squeeze, like a peg or some kitchen tongs. And participants would either see a picture and they would just simply view the object, or we presented them with the word, and they were asked to pantomime how they would use the object. So there's a little video, it's not very clear, but this is a participant in the MRI scanner pantomiming. So here they're rotating. And then we have another video on that. And we've got one of a participant squeeze it.
Yeah. So sometimes it's good to participate in these studies. Yeah. So take it out.
There's a peg. So how do we look at this data? So we essentially do a thing that is basically like mind reading. And we take really small areas of the brain, and these areas contain thousands of neurons that will respond differently to different types of stimuli. So what we do is we look at the activity pattern in one tiny area, which contains all of these thousands of neurons, and so like lots of different patterns. And we use machine learning to try and guess what the brain's seeing. So is the brain either seeing a key or a peg? And then is it a rotate tool or a squeeze tool? So basically we tried to guess whether in each area, whether we could guess whether it was rotate or squeeze. But there were also different types of tools. So it was the action that the tool, that you would perform with the tool. And what did we find? One interesting thing we found was that in our dorsal action stream, we could guess whether they were looking at a rotate or a squeeze object, even when they were just looking at the pictures. So also we found it when they were pantomiming, but the fact that we could guess in the action stream when they're just viewing shows that we automatically perceive the actions, and we're like, and even when we're not going to make the action, that's what's happening in our brain. It's automatically processing the actions that we can make onto the object. Okay, so we showed basically pictures of tools, right? And you can't actually reach out and grasp a picture. So our next sort of study that we're going to be doing is looking at real tools. And it's really difficult to do this because obviously I said earlier that the MRI scanners are just a massive magnet. And so tools like with metal in, you can't bring that anywhere near the scanner because it would just go flying. So we 3D print our tools. And I've got an example of one here. So this is like a whisk that we can use in the scanner. And we basically use a really complicated setup, which is probably one of the very few in the world, to actually get participants to reach and grasp like real 3D objects. And that's really special. It's also really difficult to do because people have to lie really still in the scanner. Otherwise, the images will come out a bit blurry. So it's a lot of work. And we get our participants, as you can see like on the picture on the right, to go in and interact with these tools. And why is this research important? Well, I guess finding out about how the brain interacts with objects is really important for developing like new prosthetics for people that have either had amputations or are paralyzed, because we can like learn how to use like brain control. And also it helps us understand the problems that are faced by people who've experienced like damage to the brain and these brain areas. And it can also assist in developing new methods for rehabilitation. And that leads me nicely on to Stephanie's talk on rewiring the brain.
No, it doesn't work.
Okay.
Cool. So thanks, Annie. That was a brilliant talk leading on to what I'm talking about. Hi, everybody. So I'm Stephanie, and I work at the UEA. And today I'm going to tell you how you can transform the science that Annie's doing into something very applied, which is to bring rehab into the home of people with brain injury. So we know that the brain can be rewired, which is very good, and your brain's changing all the time. So even you sitting there looking at me, listening to me, your brain's already forming new connections. So it continuously changes and adapts it to the surroundings. Experiences or memories even change the brain physical structure, and brain functions can move from damaged area to another, which is great because then you can utilize different parts of the brain if you've had a stroke or brain injury to do similar functions as you could do before. So in our lab, as you've heard, Hani, we study how does the brain support perception, action, and attention. So that is which parts of the brain are involved when you perceive things around you, like faces or objects, and which parts of the brain are involved when you actually interact with the world around you, and also how does your brain attend to certain things in respect to others. For example, like the whisk compared to an apple. And we're also very interested to seeing how are these kind of mechanisms in the brain perception, action, and attention affected in brain disease. So when you have a stroke, are these kind of processes impaired or spared? And can we actually use some of this to rehabilitate people with brain injury? So we go all the way from very basic science, which Annie just talked to you about, to rehabilitating people with brain injury. So let me tell you a bit about stroke, because that's what we do most of our research on. We know that stroke is really frequent, and currently there are 1.3 million stroke survivors in the UK. And one of the most common conditions that people show after stroke is something called inattention. It's a cognitive problem. We know that 2/3 of stroke survivors, once they leave the hospital, they leave the hospital with a disability. And inattention causes severe disability. And inattention is when you're not aware of one side of your body or one side of the world. So it's like you woke up and that is completely gone. And usually it's the side that you've lost your movement, so your impaired side. Your eyes are fine, so it's not like you're blind, but your brain just doesn't register that something's missing and you can't see half of the world. So I have a few examples, but let me tell you, this condition is quite frequent. It happens in 1 in 3 stroke survivors, unfortunately, and it significantly impairs rehabilitation outcome. So we know that stroke survivors, if you think about it, a stroke, you will think of someone wearing a cane. So lots of people will have paralyzed arms and legs. And we know that if you have inattention on top of that, you won't engage as well with your physical rehab. So when you're trying to improve that function of your arm. So ultimately is associated with major long-lasting disability. Also, if you ask the carers of people who care for people with inattention, it's associated with greater burden and stress And if you ask the carers, the clinicians, and the stroke survivors themselves, it's one of the top research priorities. And unfortunately, we don't have an effective rehabilitation so far. So that's what we're working on at the moment. So here's some examples. This is a drawing of one of our participants recently, and you can see that this person we asked them to draw a person, and you can see that they missed quite a lot of detail on the left side of the drawing. This person had a right hemisphere stroke. So if you have a right hemisphere stroke, also a stroke on the right side of your brain, you will have problems in the opposite side. One thing that stroke survivors very often report is that they miss things on the left. So they bump into things, or for example, they forget to eat the left side of their plate. One of our participants, her husband was very clued up about inattention, so every day he put her pills on her left. And for 10 years, every morning she asked, "Where are my pills?" So she had no awareness that she forgot where her pills were, that they will always be on her left. So you are probably sitting on your couch or in front of your computer, and if you look down, you'll see 2 hands and 2 legs. But a person with inattention, as you can see here on the right side, will only see 1 leg and 1 arm. So it's quite debilitating. So participants and patients, stroke survivors tell us it's quite frightening to have this inattention. And they can't do normal things like you and I, like watch TV, watch a talk on YouTube, or read a book, because they'll miss the left side of the screen or the page. And they also tell us that once they left hospital, they don't have enough support. So this is what we're trying to do, to bring rehabilitation into people's houses. So going back to what Annie said, how can we explain this weird, puzzling condition that happens to stroke survivors? So how does your brain see? So Annie explained that to recognize the donut, which I love, you use your ventral stream. So that's in green there. It's in the bottom of your brain, near your ears. But to reach out and grab objects, you actually use the dorsal stream, which is the one that goes to the top of your head, the parietal lobe. So perhaps we can use one of these streams to help these patients recover their attention. So that's what we're trying to do. So first we have to establish, can these patients move towards that side of space? So with their good arm, can they reach to things on their left? Maybe we could use that to improve their attention. So let's see. So we did a study. Oh, this is the lesion of the patients. So sorry, I forgot. So typically, these patients have lesion in an area called the inferior parietal lobe. So if you look at the dorsal stream, the action stream is very up the top of your brain, whereas the lesions in people with inattention tend to be more towards your ear. So it kind of maybe leaves that action stream spared. So that's what we're trying to test. Can we use these actions to improve their attention? So we did this experiment in the lab where we got people to wear these very, very fashionable goggles, always goggles in my lab. And these goggles are really cool, even though they don't look like much. But you put them on, and what they allow us to do as experimenters is that we can open and close them really quickly. So we got the participants to use their good arm, stroke survivors, to either reach for dots that appeared on a table. They couldn't feel them, they could only see them when they were illuminated. And sometimes the dots appeared on their good side, so the right. Sometimes they appear on their left side, so their bad side. And we used the goggles so they either remained open, so they could see their hand and the dots all the time, but in other trials or in other events, the participants lost vision. So the goggles closed, and they could no longer rely on vision of their hand to control their movements. And what did we find? So we tested people with inattention, which are referred there on the graph as the neglect group. We also tested stroke survivors without neglect or inattention, and we tested healthy controls. And in the different colors of this bar graph, at the bottom you can see how well they perform. So if the bars are very big, then it means they're not very close to the dots on the table. And what we found was that when the patients were reaching to the left, so that was their impaired side, they were actually pretty good. So even though they had brain injury, they had a stroke, and they had neglect, inattention, if you presented a single flash of light on the dark on the left, they could actually do it pretty well. But then what happens when you wear the goggles and the vision closes? Then we found that the patients had a little trouble with this task. So all the stroke survivors, even if they didn't have inattention, if you close the goggles, as soon as they start moving, they started to show quite a lot of errors, especially on their impaired side, the left side. And what was interesting was that this wasn't just the patients who had inattention, but this was across the board. And what we found by looking really carefully into their brain scans and seeing where the stroke happened is that these kind of errors happened when people had lesions in an area called the basal ganglia, which is kind of at the bottom of the brain, and SPOC, which, if you like Star Trek like me, you'll be very excited to hear that there's a brain area called SPOC, but that stands for superior parietal occipital cortex. So this area, it's also, both of these areas we know are really important for interpreting visual motor feedback from your actions. So what this means is that people are pretty good with inattention in reaching to very simple objects on their impaired side. But if you remove vision of the hand, they become impaired, especially if they have lesions in these places. And this suggests that to be this accurate, they are relying a lot on vision of their hand and target to reach to that target so well. So then the next slide, I'm going to show you how we can use actions, so hand actions, to improve inattention, and how we're developing high-tech tools with end users. So with stroke survivors, clinicians, and carers, how can we develop these tools so that they can use at home? And we're testing them. So one of the exercises we're working in on therapy uses balancing. So there's a video there in the corner, Annie. Annie's playing the videos for me. But we've been developing this therapy called SIGHT. And this involves balancing these rods. Very simple, 3 rods on a mat, can build it from B&Q, 10 quid. And the idea is that the patients have to reach out and lift these rods until they're balanced. So if you have inattention, you will reach out too much to the right side. So when you lift it up, the rod will be completely tilted. And most participants, when they do this for the first time, they're like, oh my goodness, what have I done wrong? The therapists don't give them any feedback. This is an exercise you can do at home yourself and monitor yourself your errors until eventually you balance the rod. So the idea is to crack this puzzle and learn to balance these objects. And we found some really promising results in a recent study in which we compared people who did this exercise, so stroke survivors with inattention, with a control group who did a very similar exercise but didn't balance the rods at all. They just lift the rod up and put them back down. And what I'm showing you on these graphs is their kind of inattention scores. So the bigger the bar, the more the improvement they have on their inattention. And what we found is that not only they improved in, for example, marking middle of lines, but they also improved in their visual search. So they started finding more things on their impaired side. Obviously, this was a really small study, so a very small trial. So now we're trying to replicate this with a larger group. But this therapy, even though it's really simple and only costs £10, is actually really difficult to do on your own if you have inattention, because for different times you have to use different rods, and there's a list and you might forget the instructions. So what we've done is we paired that with a really cool industry partner and tried to develop into a computer game. And why use tech? Well, tech is great, the patient tells us, and doing these kind of exercises because it increases your self-efficacy. So stroke survivors tell us that when they're doing therapy themselves for their cognitive problems, they feel like they're succeeding and they get really a lot of reward from it. They also find these kind of exercises more engaging than just the rod and the mat. So doing it via computer is more exciting. From a clinical point of view, the clinicians tell us this is better to monitor rehabilitation. And indeed, we can feed the data back to the NHS. So therapist Anna could monitor John, whether he's doing his homework every day, and check how well he's progressing and adjust the levels, for example. It also saves money to the NHS because there's less traveling to people's homes and you have a lot of data, so it increases efficiency. So how do we go about developing tech? So we develop tech by working with industry partners, and then we also invite end users. So if you're interested in helping with our research, we can do this remotely as well online. So we ask end users, and by this I mean stroke survivors, brain injury survivors, for their opinions about the tech we want to develop. And we run kind of focus groups and interviews. Then we use their opinions to refine our prototypes. And then we do small trials in which we take it home, like version 2 of the prototype, see if it works, see if it does what it says on the tin. And more recently, what we're doing is we're running a large feasibility randomized control trial. So that's a large control trial. We don't know which group people belong to, and this is funded kindly by the Stroke Association, and it's running across the whole of the east of England. So if you know anyone suffering from inattention, we're very happy to come in and deliver the trial there. So why is it important to develop technology with end users? Well, it's really important because you want to make sure that people are going to use the tech you develop. And that's been a big problem in cognitive rehabilitation, the field I work with. So as you notice, there's 65 published clinical trials, and none of them show any effects. So perhaps it's because these therapies were developed without people who actually suffer from the conditions to actually tell us what they think about it. So it's really important to engage with end users so that you develop something that is meaningful to them, a bit like here in this joke of a picture. So let me show you what we've done. So I showed you the rods and the mat, but here I'm going to show you the computerized version. So you can see Elise, which was a brilliant former student of ours. She's standing in front of the television with a small motion tracking. I think you can hear the instructions now.
Repeat rod lift until it's balanced.
And in essence, the motion tracking is counting the number of lifts, as you'll see. So it goes bling. So as you can see, this will allow for someone to sit in their living room in front of their telly, have a motion tracking there, and we can record how many lifts they're doing until they'll balance the rod. And we can also deliver these written and auditory instructions. So it makes it much easier for stroke survivors to develop their own therapy and run their own therapy. So how did we do testing this in the real world? So I'm showing you some photos here and the data that we've been getting so far. So you can see this is a converted barn, which is typical in Norfolk, where we are right now. And what we find is that on average, in a small study we ran, we were getting people to balancing rods about 1,000 times over a week. So that's a really good number of repetitions. So just like when you're learning to play tennis or golf, you need to repeat. So it's the same in rehab. You kind of have to be prepared for kind of a good fight. And what we found is really promising is that this was again a small study, but we found that this started participants who did this intervention with a computer, they actually started to look more to the left after the training. So we found that their visual search was better, and they started to find more things on the left. What we've also done is, because we want to measure whether our therapy works and kind of the same setup as we're doing the rehab, we've developed a new test for neglect. And it's really important to develop methods to assess this condition because it's significantly underdiagnosed. The tests we have at the moment in the clinic are just A4 sheets of paper. That doesn't give you a lot of data. It just gives you correct and incorrect. But if you have a computerized task, you can actually measure how fast people are finding things on the left. So it's much more sensitive. So I'm going to show you what we've done here. And you can come to the forum and try this because we've got it there.
Some mugs will be complete and some will have a gap on the handle. Please click all the complete mugs, those with no gaps.
Okay. Oh. Great. So you can see that gorgeous Elise here is kind of doing a task like find Wally. So that's the idea. She's trying to find these mugs that are complete and ignore the ones that are broken. And we'll run this on people's houses. So we take all of this kit into people's houses across East Anglia to do this study. Then we have another task in which we ask participants to mark the middle of lines. So you can see we have this small camera as well in front of the telly, and that talks with the remote control, so we can measure where you're clicking.
Horizontal lines of different lengths will appear in different places on screen, one at a time. Once the line appears on screen, please click using the mouse where you consider the center of the line to be.
Great. So what Elisa is doing here is trying to find the middle of lines. And as you know, if you have inattention, hopefully by now you'd guess people have problems with this task. So yeah, so we've developed these two tests. So after they do the rehab and before we can do these things to try and measure the effect of rehabilitation.
Horizontal lines of different.
Okay, so let me show you some preliminary data here. So on the left-hand side, you've got a control participant, so that's just like you and I. And you can see that when they're trying to find these mugs, they do a nice kind of left to right pattern, like when you're reading left to right. So that's a normal, healthy visual search pattern. Then you can see a stroke survivor with neglect or inattention, and it took them 4 minutes to do this. They couldn't find most of the things on their impaired side, the left. And if we move along, I'll show you this is someone who's recovered. So you can see, obviously, they're finding many more mugs here, but it's very disorganized. It's not a nice, neat left to right pattern. So we're hoping that compared to the traditional, paper and pencil tasks, because we can produce all of this rich data with time and maps of search, it could be much more sensitive to detecting inattention. And we've collected data also from a large sample of healthy people, actually here at the forum a few years ago. And Annie will show you this in a minute. So this is Amy and Siraj, who did all the data collection at the forum. These are all the age groups we tested, so 179 people did our task. And what's interesting is that, if you click again, sorry Annie, is that age, this is a correlation. So what's the relationship between like age, education, and the data we're getting from our Find Wally kind of task? And you can see that age significantly correlates with how long it takes you to find the items and how high quality you are, how successful you are. And it also, the two tasks, so the visual search and the bisection, are very related to each other. So this is really promising because previous studies had found that these kind of tasks are not so sensitive to aging. But our task, we think, is much better, of course, because it's far away. It's in a big television. So it's more like the real world kind of search you would do in your daily life. And because it's sensitive to aging, we'd like to test this also in people who have cognitive impairment and dementia. So that has really promising results. So currently, as I said, Helen Morse, who's funded by the Stroke Association, and I are running a large clinical trial across the whole of East of England. So all these lovely people in these hospitals, the clinicians, are recruiting stroke survivors for us. So we're working with an NUH, Norfolk and Norwich, the Norfolk Community Health and Care, Addenbrooke's, and also the East Coast Community Health Care. And we started the trial in May for obvious reasons, which I won't mention. And we trained so far around 8 therapists to deliver the C-site themselves. We don't go in the research team. NHS clinicians are actually setting up all the kit in stroke survivors' homes. And so far, we have 15 patients into the trial. I don't have the results yet, so watch this space. Maybe next year, I'll show you some data. So how does it work, though? What exactly is happening? So we have an hypothesis, as I kind of hinted before, that because these people with inattention, they're quite good at doing actions, potentially we think that they could be using their action stream, so the dorsal stream, the one that ends in the parietal lobe, to do this task. And this is kind of to balance these objects. what we think is this stream is really important. So they have to self-correct themselves to reach the middle. And we think that learning to grasp objects correctly is a dorsal stream function. And perhaps these areas are helping people improve from their attention. So, and we've done a study, a bit like Annie showed you earlier, which just got published this year, where we used the crazy setup in the MRI scanner, as you can see here. This was led by a brilliant PhD student of mine, Ethan, who's now at the MRC in Cambridge. And what we found was really interesting, was that there are certain areas of the brain that really care about looking to pictures of hands and tools. So just by watching the telly and seeing pictures of tools and hands, there are certain areas of the brain that really care about these images compared to other objects or faces, for example. And we found that we could use these mind-reading methods that Annie talked about to actually decode whether people were grasping tools correctly. So we think that these areas might be really important for our therapy. And this is actually quite important because if we know what areas the therapy needs, that we could target specific patients for specific therapies. So we could make sure that the patients who do the rehab site, they actually have these areas spared. So that's one way we'd like to investigate. So more like personalized medicine. So next, I'm going to tell you a new improvement, a new technique that we've been trying to use, which we're trying to use eye movements, and we're very early in the development stages. So here, we're using something called Pursuit Eye Movement Training, and we've developed an app in which this kind of uses these kind of psychedelic stimuli. So Annie will play the video, you'll see how it works. So it's kind of like when you're sitting on a train. It doesn't work? Not to worry. I'll show you in the next video. You could maybe move on to the next slide. There's a video there. So here the idea is that you're staring at the screen and probably you're getting this. You can't stop your eyes from moving. And this is using very kind of primitive structures in your brain to trigger these automatic eye movements. So we've developed an app with the brilliant folk at Animorph in London, and the idea is they have this tablet at home and it has a webcam in the middle of the screen, and it's using machine learning to classify if people are doing the eye movement correctly. So we're getting people with inattention to move their eyes automatically to the left by playing this kind of game in the tablet. And the more they look to their impaired side, the idea is that they would improve more in their normal function of daily life. Yeah, so that's me. I just want to say we're at the forum upstairs. We have a stand called Explore the Brain in Action. And if you want to volunteer for our research, we're always looking for participants. So you can email us at neurolab@uea.ac.uk. And finally, I would like to thank the brilliant people, including Annie, who you saw today, but also Alan and all of the other students who we've worked with before, the clinical sites, the funders, and our industry partners. I hope you enjoyed the talk with us today. Bye. Oh, we have questions. We're not done yet.
So, Jonathan from Edinburgh. So, this one's for Annie. Why the difference between kitchen tools and other tools?
So the question is, do you want to sit here? I think.
Was this in the task?
Yeah.
Can you see me?
Yeah.
Okay, so
repeat the question.
yeah, was the question about why in the task did I ask people to grab kitchen tools with their left and tools with their right? Okay, so the purpose there was that was completely irrelevant to what the task was. Okay, so I wanted you to grasp the kitchen tool with your left hand and a tool with your right hand, and you didn't know at the time that the handle of maybe the frying pan you saw was facing the left side, and in that sort of trial or like example, it would be easy. But if the handle of the object was the other way, it's a bit more difficult when I said, can you grab a kitchen tool with your left hand? So the fact that that's really irrelevant shows that it's an automatic process in the brain, that we're automatically like want to reach and grasp with the hand that the handle's pointing towards.
Great. And Rosie asks, if someone has inattention and you actively draw their attention to the side where they have inattention, can they see and engage then?
Yes, so that's a really good question. So This is a therapy actually that is used in the clinic. So the therapists currently in the NHS spend a lot of time cueing the patient to look to the left. But the problem is that the brain doesn't register that it's missing something. So this therapy actually doesn't work. But on the spot, if you tell someone, look, you've drawn only half of someone's face, they're like, oh my goodness. So they're really surprised. But it doesn't work in the long term, and it doesn't generalize to daily life.
And Rosie has also asked, does inattention differ for people who are left-hand dominant?
Yes, there's a few studies of stroke survivors who are left-hand dominant compared to right-hand dominant, and it shows that our hemispheres. So in the brain, there's two hemispheres, and we know that the right hemisphere is dominant for attention. So if you're right-hand dominant, and that might differ if you're left-hand dominant, it's not straight kind of clear picture, but there is some evidence that handedness does affect brain lateralization. So that's a great question. Cool. So that's it. So I think that's it from us. Thanks for coming to meet us. Thanks, Annie, for a great talk. And yeah, hopefully see you upstairs at the forum. If not, yeah, reach out if you want to help out. Bye.